Why, hello. Today we're going to go on with section 16.3, which deals with double integrals over general regions. In section 16.2, what we dealt with was double integrals just over rectangular regions, where the order of integration really didn't much matter. Today we're going to look at regions that look like this or that look like this. So let's look at this one first. The mentality in setting up your limits of integration when you have a region that looks like this is very much like what we did in chapter 6 back in Calculus 2. You ask yourself, how shall I draw my strips? Perpendicular to the x-axis or perpendicular to the y-axis? Now, and think of it in terms of if I was going to find the area between the two curves, how would I draw my strips? Well, you want to draw your strips so that the strips uniformly go from one curve to the other curve. So if I draw my strips this way, you can see all of them go from the red curve to the green curve, which is G1 to G2. And if we look at one arbitrary strip, okay, we look at that strip, notice what we're going to do is you pick an arbitrary x in the region between A and B. Pick an arbitrary point between A and B. And notice no matter what point I pick between A and B, if I let the y range, the y is always going from the green curve G1 to the red curve G2. And so my limits of integration here is going to be, it's going to be some function f of x, y. Y is ranging. We're going to let y range from, now what's y ranging from? The lower bound to the upper bound. So y would be ranging from G1 of x to G2 of x. And after we sum up, from going from G1 to G2, we're going to take each of these strips, each and every one of these strips, and sum those up. And as we sum those up, what's x ranging from? X is ranging from A to B. Okay, so you ask yourself, how can I draw my strips so that my strip uniformly goes from the one curve to the next curve? That's going to be your inner integral. My y is ranging from G1 to G2. And then if I take all of those strips and sum up those integrations, what is that sum going? Now I'm going in the x direction. My x is going to be ranging from A to B. And the keys to the kingdom are deciding which way shall I go first, with respect to x or with respect to y first. In this picture right here, again, drawing strips perpendicular to the x-axis would not make sense. If I draw a strip like here, I'm going from blue curve to this red horizontal. Here I'm going from horizontal to horizontal. Here I'm going from horizontal to another blue curve. Strips perpendicular to the x-axis would not work. On the other hand, if I draw my strips this way, okay, if I draw my strips this way, and let's look at one thing, notice, pick an arbitrary y in your domain, an arbitrary y between C and D, and ask yourself, if I take that arbitrary y between C and D, what is x ranging from? Well, I'm going from here to here. So my integral, the inner integral is going to be x. What is x ranging from? The lower limit is h1 of y. The upper limit is h2 of y. And after I take each of these strips, each one separately, and sum all those up, if I sum up those integrations, my y is going to be ranging from C to D. And that order of integration would give you the function over that region, which I have in yellow, of f of x dA. Okay? All right, now today, the thing is, notice I just have the region. I'm integrating over the xy plane. And this f of xy is z equals f of xy is some roof that's over on top of that. Everybody understands? That's what we were talking about the other day. Now I have found, as long as you're assured that your roof is totally above the xy plane, and in today's homework every time it is, all right, what you really have to worry about is your xy region that you're integrating over. And it really is much easier if you draw your xy region in the xy, just with the xy, and don't even worry about the surface over the top. All right, now in this one here, it says evaluate the integral over some region D of x plus 2y dA, where D is the region bounded by the parabolas y equals 2x squared and y equals x squared. Now some of these I'm going to actually put on the calculator to help us do the graph, but I think most of you know what y equals 2x squared and y equals 1 plus x squared looks like. So let me draw it. Y equals 2x squared. I don't like that pen. Let me get one that's a little bit, that was a new one though, unfortunately. Y equals 2x squared is an upsy parabola. Okay, and y equals 1 plus x squared is an upsy parabola that's going to be a little bit wider. No, that's not too good because it's got to come whoop right up here also, okay, so that it's nicely symmetric, all right. This right here is y equals 1 plus x squared, and this right here is y equals 2x squared. So what we have is this region. Now, it's imperative before we actually set up our integration is to get the important corner points. So we have to know what this point is and what this point is. And I could put it on the grapher and we could use the intersect key, but I also could say, wait a second, this isn't that terrible. I have, at this point where the two curves intersect, I have 2x squared equal to 1 plus x squared, right? The y coordinates are equal. If I subtract x squared on both sides, I get x squared is 1, or x is plus or minus 1. So I bet you this point has a y coordinate of minus 1, and this point right here has a y coordinate of 1. And since these 2 points are on both of the curves, I could take x equals 1 and plug it into this curve or this curve. Plug it in here, you get 1 squared is 1 times 2 is 2. You get the same thing here. Now we have to ask, to set up our limits of integration here, how shall I draw my strips? As you can see, if I draw my strips this way, letting x range first, the problem is you're going from the same parabola to the same parabola. We want our strips to go this way. Notice this point right down here is x is negative 1. This point right here is x is 1. So we look at an arbitrary x, and we ask ourselves, what is y ranging from? So you pick an arbitrary x and look at the strip that goes perpendicular to it, and what is y ranging from? So we're going to be integrating x plus 2y dy. Well, what is y ranging from? Y is ranging from the lower curve is right here, which is the function 2x squared, to the upper curve, which is 1 plus x squared. So our limits of integration are going to be from 2x squared to 1 plus x squared. And then we're going to take each and every one of those strips with our integration and sum up all of those. And what is x ranging from? Well, from the lowest strip to the highest strip, x is ranging from negative 1 to 1. Are we doing okay? It's very important for us to draw the picture. All right? Where did the, oh, it came right from here. That's your z equals f of xy. That's your rooftop, okay? All right, but they're just giving you that. But they're saying if you're doing this integration of this function over this region, and this is the region that's bounded by the parabolas y equals 2x squared, y equals 1x squared. This is given. You have nothing to do about that. You just bring that down. But you're going to look at your region, and D is the region that's determined by these two curves. Okay? All right, now, we have a lot of integration to do, so I don't know how many I'm going to go through all the way. But this one, let's just practice. We've got to do the inner integration first. Okay, and if I do the inner integration first, I'm taking the integral of x plus 2y dy as y goes from 2x squared to y equals 1 plus x squared. Now, some of you were coming into my office this morning or yesterday, and you were struggling a little bit with doing this integration. You said, yeah, I was doing okay with partial differentiation, but this partial integration is giving me trouble. If it's giving you trouble, what I suggest you do is look at your integral. And since y is what's changing, x is constant. So if you want, put a constant in for x and say, what would I do? Just to help you think about what you would do in terms of that. But this one's a pretty easy one. So let's see, if I'm integrating with respect to y, this is like 5, so it would be 5y. So it's going to be xy plus the integral of 2y y is the variable, with respect to y is y squared. But notice our limits of integration are as, since this is with respect to y, as y varies from 2x squared to 1 plus x squared. It's very important to write this because otherwise, in a couple sections we're going to be doing triple integrals. And you're really going to be going wacky in terms of x, y, and z. What am I plugging in, for my limits of integration? Now at this point, we're taking our upper limit, 1 plus x squared, putting it in for y. So we have x times 1 plus x squared plus y squared, which is 1 plus x squared squared, minus, parentheses, 2x squared is going in for y. So I'll have x times 2x squared plus 2x squared squared. Everybody with me? Okay? Now time is of the essence, and I don't want to bore you to tears with multiplying things out and combining similar terms. And if you're in Calculus 3, you can do that. So I already took the liberty of doing that, and I ended up getting x minus x cubed plus 1 plus 2x squared minus 3x to the fourth. Just multiplying things out and combining similar terms. So now what are we going to do with that? That's part 1. So we take part 1 and we say this is going in for this. So now we have to do the integral from -1 to 1 of x minus x cubed plus 1 plus 2x squared minus 3x to the fourth dx. Okay, and to do that, you're going to be integrating with respect to x. This is a Calc 1 problems. You'll have 1/2 x squared minus 1/4 x to the fourth plus x plus 2/3 x cubed minus 3/5 x to the fifth. And we've got to do it from x equals -1 to x equals 1. Okay? And then again, you're going to plug in 1 in for here, minus plugging in -1 in for here. So plug in 1 minus plug in -1, and I'm not going to do it because, that's tedious arithmetic. And what we'll end up getting is 32/15. Okay, there's a lot that I want to spend on the calculus today, not the tedious calculus. Okay, tell a Calc 1 class that that's tedious and they'll be horrified. Okay, are we doing okay? All right, we got to do another one then. Next one we got to do, and even though I say it's the you people very well should probably leave some space, and before you even start doing your homework, go back and do the examples. Some students, in fact, do they'll do the homework as the examples, and then they'll do like 5 or 6 from the chapter that they have time to do. That's another way to study, go back over what we've done in class. Okay, now in this one, they want us to evaluate the double integral. Notice they're saying x is ranging from 1 to 2. We're taking this function, 4y over x cubed plus 2, and we're integrating over some region, which they're calling D. And D is described as all the ordered pairs x, y, all the points, for which x is ranging from 1 to 2, and y is ranging from 0 to 2x. Now, one way to do these is you could say the one that's varying from something to something in terms of x is going to be your inner limit, and the one that's ranging from a constant is going to be your outer limit. So I could say to you people, it's real simple. Since y is ranging from 0 to 2x, that's going to be your inner guy, and then your x is ranging from 1 to 2, that's your outer guy. I'd like to take a second, though, just to draw the region so you can understand why the limits of integration are as they are such. All right, so let's look. I'll bring that back out in a second, but let's look. What they're saying here is y is ranging from y equals 0. What does y equals 0 look like? It's the horizontal line. It's the horizontal axis, so that's y equals 0. To y equals 2x. What does y equals 2x look like? It's a line. Okay? On the flip side, x is ranging from x equals 1 to x equals 2. Well, x equals 1 looks like this, and x equals 2 looks like this. So my y's, if I pick an arbitrary x between 1 and 2, my y's are ranging from y equals 0 to y equals 2x. we sum up all those strips as x ranges from 1 to 2. This is what the region looks like that we're integrating over. And so that's why if you draw your strips perpendicular to the x-axis, look at one arbitrary strip, pick an arbitrary x. What is y ranging from? Y is ranging from y equals 0 to y equals 2x. And then if we sum up all those strips, your x's are ranging from 1 to 2. All right, so what's important for us to do right now is we're going to do the inner integral first. So the inner integral is the integral from 0 to 2x of 4y over x cubed plus 2 dy. Remember, x is right now being considered a constant. X is being considered a constant. Okay? So if x is a constant, you can factor that constant out, can't you? So this is equivalent to 1 over x cubed plus 2, integral from 0 to 2x of 4y dy. And we're integrating with respect to y. So this is 1 over the constant x cubed plus 2 times 2y squared as y ranges from 0 to 2x. Keep your constant on the outside. And we're going to plug in 2x for 2y squared. We're going to plug 2x in for y. And we're going to plug in 0 in for y. And so this looks like it's 1 over x cubed plus 2 times 2 squared is 4 times 2 is 8. And then we'll have x squared, which I guess I'll write as 8x squared over x cubed plus 2. Okay? Very important. Now it's important for me to take this, because that's just the first integral, and that goes in place of this. Okay? So, we're going to plug in. We're doing the integral from 1 to 2, but the inner integral is going to replace with 8x squared over x cubed plus 2 dx. All right, and now this is a Calc 2 problem. How do I do that integration? Well, first of all, 8 is a constant, so I can bring that out front. How can I attack that?
U equals cubed plus 2.
If I let u be x cubed plus 2, notice du is 3x squared dx. So notice x cubed plus 2 is u. Now, there's multiple ways. You have x squared dx to deal with. If you want to deal with x squared dx, if you'll notice, your x squared dx, if I divide by 3 on both sides, is 1/3 du. So I can replace my x squared dx with 1/3 du. And I think I'll put the 1/3 out front and the du inside. You can always move a constant out front. What is the integral of 1 over u du? Natural log. So I have natural log of, it should be absolute value u, which is 8/3 natural log of u was x cubed plus 2. And we're evaluating it from x equals 1 to x equals 2. And natural logs I always like to go over because students tend to not have learned them as well as they should have in Calculus 2. You learn it for the test and then you forget. I always, if I have a constant times a function, I like just to factor him out. And then if I plug in a 2, I will get the natural log of 2 cubed is 8 plus 2 is 10. I can drop the absolute value because 10 is positive, minus natural log of 1 cubed is 1 plus 2 is 3. And remember, natural log of a minus natural log of b is natural log of a over b. So this just cries out that we write this as natural log of 10 over 3. Okay. Any questions? Okay. Sure, you could do that. Equals natural log of 10/3, the whole thing raised to the 8/3. And that'd be using that 10 log a is log of a to the n. Notice just a is being raised to the n, not all. By the way, this is one thing I see on tests all the time. People This has nothing to do with Calc 3, but there's a big difference between log of 2 to the third and log of 2 to the third. This one, all of log 2 is being raised to the third. You can't bounce that exponent down. Cubing something is not the same as multiplying it by 3. But if you just have the log of 2 cubed, you can bring the 2 out front. Because you all know cubing something is not the same as multiplying by 3. But taking the log of something cubed is the same as multiplying 3 times the log of that number. Okay, let's do one with trig, because trig is something that we tend to struggle with. Again, we're integrating over some domain. The domain is bounded by, and we got to draw, you have to draw it to get an idea what it looks like. Y equals 0 is the x-axis, so this is y equals 0. Y equals x squared, I know what that looks like. That's what y equals x squared looks like. And also x equals 1, that's a vertical line. Well, if we have the regions bounded by the x-axis, y equals 1 and y equals x squared, I think it's going to look like that region. Now, to tell you the truth, I could draw my strips this way, or I could draw them this way. We could do it either way, but for most students, if it's going to work going this way, let's go this way first. So we're going to pick an arbitrary x and look at our strip. And notice no matter what strip I draw in that region, over here or here, if it's vertical, they're going to be going from the x-axis to the parabola. So what are we going to be integrating with respect to first? Y. We're letting y change. So what's my y? Now, what's my function I'm integrating? It's x cosine y. They're just giving me that. So we're integrating the function x cosine y as y ranges from, what's y ranging from? Y equals 0 to y equals x squared. And if we sum up all those strips in the region, x is ranging from 0 to 1. The keys to the kingdom are setting up your limits of integration. That's what this section's all about. But definitely you want to practice. And you're not going to be able to sit down and do this in one sitting. You know, you're going to do 2 problems here, 2 problems there, 3 problems there, you know, because it gets a little bit tedious. Okay, so what do I have to do first? First, I'm going to do the inner integral, 0 to x squared of x cosine y dy. That's the first thing I have to do. Now, the beauty of this is I'm integrating with respect to y, so x is a constant. So I can just factor that darn thing out. And I think we all know the integral of cosine is sine. And don't just put from 0 to x squared. It's as y ranges from 0, y equals x squared. Because you can end up plugging in for the wrong variable. So x squared goes in for y, and 0 goes in for y. But the sign of 0 is 0, so we just have for our inner integral x sine x squared. Okay? I'm going to take that and plug that in for my inner integral. So I will have the integral from 0 to 1, and I'm going to write this as sine of x squared times x dx. Okay, I'm going to put that x at the end. And you guys know perfectly well why. Why? Because I need a u substitution, absolutely. We're going to let's just move this over a little bit so you can see it a little bit better. We're going to let u be x squared. So du is 2x dx. You can put a 2 here and a 1/2 here if you're uncomfortable with that. I have an x dx I want to get rid of, multiplied by a half on both sides. So 1/2 du is x dx. So this integral becomes, notice I don't put the limits of integration here because that's as x goes from 0 to 1, not what u is doing. So I'm going to make it be sine u. And for x dx, I'm going to replace it with 1/2 du. And I think everybody in here knows how to integrate sine. The integral of sine is going to be 1/2. Integral of sine is minus cosine. Check yourself. If I take the derivative of this, I should get that. Derivative of cosine, all the co-functions have a minus for their derivative, so it's minus sine. So it's minus a minus, which gives me a plus, which gives me minus 1/2 cosine. What was my u? My u was x squared. and we're integrating from x equals 0 to x equals 1. And so I have, again, if I have a constant, I just like to factor him out, don't have to carry him along. So if I plug in a 1, I get cosine of 1 minus cosine of 0, which gives me minus 1/2 cosine of 1, and cosine of 0 is 1. That's my answer. Now your book takes the minus and distributes it and writes it as 1 minus cosine 1, which is fine. They're both fine. Any questions? Nope. All right, then let's go to look at the next one. Okay, in this one, they want us, D is the triangular region with vertices 0, 0, 1, 2, and 0, 3. All right, so we got to draw that triangular region. The first corner is 0, 0. The next corner is 1, 2. And the other one is 0, 3. And we're talking about this region. Unfortunately, they gave us no equations. The easiest thing to do, though, is to say the following. I know the equation of any line is y equals mx plus b. So what I'm going to do is I'm going to find the slope of each of those. Now, this line right here that goes, and this is 0, 0 here, by the way, and this is a 1 here because you went over 1 up 2. If I want to find the equation of the line that goes between, the equation of any line is y equals mx plus b. B is the y-intercept, m is the slope. Well, let's look at this line right here, the one that's descending. Its slope is change in y over change in x. Well, it's going to be 3 minus 2 over 0 minus 1, which gives me 1 over a negative 1. Its slope is negative 1. So its slope is minus 1. And geez, this one's so easy. The y-intercept is 3. I think it'd be easier to write it as y equals 3 minus x, but that could be the equation of that line. Absolutely. And check. If I put 0 in for x, I get y equals 3. If I put 1 in for x, 3 minus 1 is 2. I get y equals 2. Yeah, I got the right equation. So the equation for this line right here is y equals 3 minus x. Now I have to get the equation of this line. Again, I want to use y equals mx plus b. I got to get the slope. Slope is change in y over change in x, so it's 2 minus 0 over 1 minus 0. That's 2. So it's going to be y equals 2x. But what's its y-intercept? 0. So its equation is y equals 2x. Now we have to decide how are we going to draw our strips. If you decide to draw your strips this way, you can do that. But guess what? You're going to have to break your region up here and do 2 integrals. Because if you pick an arbitrary y and let x range, up here the x's are ranging from 0 to 3 minus x. Well, no, I have to solve for x. Okay, it would be x equals 3 minus y. Here, the x's are ranging from x equals 0 to this line. 0 to top line, 0 to bottom line. It would be 2 integrals, and you're more than welcome to do it that way. Sometimes you have to do 2 integrations, but I think good mathematician's a lazy mathematician. Let's draw our strips this way. If I draw my strips this way, what is y ranging from? First of all, I forget the function I'm integrating. It was 2xy. So what are we going to integrate with respect to first? dy. What is y ranging from? Y equals 2x to y equals 3 minus x. And then if I sum up all those strips, x's are ranging from 0 to x equals 1. Okay? Again, we have to do the inner integral first. We're integrating from 2x to 3 minus x, 2xy dy. X is a constant, so it just comes along for the ride. So my integration is going to be x y squared. Because if I take the partial with respect to y, I better get what was inside, and yeah, I do. Bring your 2 down, 2xy. And this is going as y equals 2x to y equals 3 minus x. If you plug a y in, 3 minus x in for y, you're going to get x times 3 minus x squared minus x times 2x squared, because we're putting 2x in for y. Okay? You've got to multiply this out, multiply by x, square this, multiply by x, combine similar terms. I did that already. You guys are more than welcome to fill in the blanks. You're going to get 9x minus 6x squared minus 3x cubed. So what do I do with that? I take that and I plug it back in for the inner integral, this guy. So now we have the integral from 0 to 1 of 9x minus 6x squared minus 3x cubed dx. You guys know how to do that. That's not the part that you're learning today. You know how to take the antiderivative of that, plug in a 1, plug in a 0. Take my word for it, after a while, 5 minutes later, we'll have 7/4. Okay? I'm doing this so that we have plenty of time to look at lots of regions instead of tedious Calc 1 stuff. You wouldn't be here if you didn't know how to do Calc 1. Okay, we did that one. Let's do another one. Okay, now things are going to be getting interesting. In this one, they're not giving me the integral. What they're giving me is they're asking me to find a volume. Find the volume under the surface z equals 2x plus y squared. That's above, this is my roof, and it's above the region bounded by x equals y squared and x equals y cubed. Now, in all of these that you have in your homework tonight, the z equals is your rooftop. Okay, and you guys know very well from all the ones that we've done, if you have your rooftop, I don't know what my roof, what this curve looks like. It looks something like this, let's pretend. And if this is z equals, let's say, f of xy, and there's some region down here, r, that I want to be my floor, and then I bring perpendiculars up, you with me, to make some kind of cylinder, and we want to get the volume. Every single time, my volume is my rooftop times dA. And that dA could be dx dy, or it could be dy dx, every single time. Now, in a couple more sections, the problem is going to be, this is not always above the surface. It could be come down and intersect the surface. But in this particular homework, it is. Let's look at, and each time when we look at the region that they're talking about that it's bounded by, let's talk about how do we know that it is going to be above the xy plane. First of all, I'm going to draw these two. We have x equals y squared and x equals y cubed. This one, if I solve for y, is y equals plus or minus the square root of x. This one, if I solve for y, it's y equals cube root of x. Okay? If I draw it, the one, y equals plus or minus the square root of x, you can go this way. Okay? And you also could go this way. Okay? Cube root, now you think about it, the cube root of a number that's less than 1 is greater than its square root. Okay? So cube root is a little bit higher, like that, and then it intersects and goes like that. All right, so my picture's sort of hard to see. You redraw it just a little bit. You have the one going like this, and the other going like that. This one is y equals square root of x, and this one is y equals cube root of x. Okay, and this is my region. By the way, where are they intersecting? What's the point of intersection? 1, 1, very good. Because if you put a 1 in here, cube root of 1 is 1, square root of 1 is 1. We could do our strips perpendicular to the x-axis, perpendicular to the y-axis. Either way we could do it. Which way do you want to do it? Perpendicular to x. Yeah, when in doubt, always do x. If you have to do y, you do it that way. All right. Because this is, I pick an arbitrary x. Now please notice, the rooftop is z equals 2x plus y squared. My whole region's in the first quadrant. x and y for every point in the first quadrant's positive, z's positive, this surface is above the xy plane. So we don't have to worry about what it looks like. All right, so what we're going to be doing is we're going to be doing the double integral of 2x plus y squared, because that's my height. Notice, we're going to go, you told me you're going to do this kind of strip. So if we do that kind of strip, y is ranging from, and then x is ranging from. Please notice, people, the beauty of this integral. What is this giving you? I mean, I'm going to set those limits of integration in a second, but notice what you're doing. You're going sum, sum. The 2x plus y squared is your height, and then you go times delta x times delta y. Delta y. Do you see? You've got your surface like here. You've got your region down here. You're cutting them up. And you take this one little delta x, delta y, and you bring them up here. And when you go delta x, delta y times height, what are you getting? Volume. And then you're summing up all in the x direction, summing them up all in the y direction. You're summing up all the little delta volumes, and you've got the total volume. That's what you're doing. So it's height times width times length. Now, you guys tell me, what's y ranging from? Square root of x to cube root of x. And then if I sum all those up, what's x ranging from?
0 to 1.
Pardon?
0 to 1.
0 to 1. Okay. What if instead I decided to go with respect to x and then with respect to y? Let's do that. Let's set it up that way also. Okay? Because I'm thinking, who wants to plug in square root of x, cube root of x? If I did, let me redo my region one more time. The one goes like that, and that was y equals cube root of x. And then the other one went okay, and this is 0, 1. What if instead in the function I'm integrating is 2x plus y squared? What if I wanted to go with respect to x and then with respect to y? What if I wanted to do that? Then we would say, how is x varying? So you pick an arbitrary y, and you're doing this, right? This curve right here is y equals cube root of x. So what's x ranging from? You've got to solve for x, don't you? Cube both sides. X equals y cubed. And this curve is y equals square root of x. I'm saying, what does x range from? X is ranging from y cubed to the green guy is x equals y squared. So x would be going from y cubed to y squared. And if I take all those horizontal strips and add them up, what is y ranging from? My lowest y value is 0. My highest value, that's not 0, 1, that's 1, 1, by the way. My highest y value is 1. Now, we're not going to go do both. We're not going to do this integration and in this integration. But guess what? If you did this one and you did this one, should you get the same answer? Yes. Which one do you think looks easier to do? What's going to happen is sometimes you're going to set up an integration and you're not going to know how to do it. You're like, oh, a substitution's not working. Ew, I have no idea how to do this. Or if you change the order of the limits of integration, it might be something that falls flat in your face very easily. So that's what my point is. You don't have to, sometimes you can do it either way, but one way is the only way to do it in closed form. Both of them you could put into Maple, and Maple would come up with a nice answer, all right? But with paper and pencil, sometimes it's not too obvious. Okay, let's do this one right now. I have to do the inner integral. This is a pretty easy one, isn't it? I'm not going to do it. You want me to do it? You want me to do it? Okay. We're going to go from y cubed to y squared, 2x plus y squared dx. Remember, right now, y is the constant. Integrating with respect to x, so the integral of 2x is x squared. Y squared is acting like a 5. So that the integral of 5 dx is 5x, so it's y squared x, or xy squared. And we're going from x equals y cubed to x equals y squared. So what are we doing? Where I see x, I'm taking it out, and I'm replacing x with y squared. Where I see x, I take it out, and I replace it with y squared. So this is plug in the top minus where I see x, I take him out, replace him with y cubed. Where I see x, I take him out, replace him with y cubed. So this gives me y to the 4th plus y to the 4th minus y to the 6th minus y to the 5th. And all of that is going in for my integral. Taking that and plugging him in here, I am now going to evaluate the integral from 0 to 1 of, I'll write that as 2y to the 4th minus y to the 6th minus y to the 5th dy. You guys can finish that. You know how to integrate that with respect to y. It's a bit tedious. I suggest once you get the obnoxious fractions, put them in your calculator and just hit math code of fraction, because you're going to end up getting 19 over 210. Okay? You guys know how to do that. If you don't, come see me. And I'll be worried. We might put you back in Calc 1. Okay. All right, let's look at the, oh, by the way, this isn't essential for us to do the problem. We verified what the region looked like in the xy plane. We verified that the surface is hovering over the top. But I took the liberty of putting in the surface z equals 2x plus y squared in Maple. And I took the liberty of telling it to sketch the curve x equals y squared and x equals y cubed in the xy plane. And this is what the graph looks like. This is what the intersection of those two surfaces looks like, those two curves. And this is the surface above. Okay, and you guys are going to be getting a worksheet showing you how you can do that. And what's neat is when you do it in Maple, you can actually click on it and have it change, you know, and to be able to view what it looks like from different angles. Okay, let's do the next one. The next one we have z equals x squared plus 3y squared. What does the graph of that look like? What is that? What is the graph z equals x squared plus 3y squared look like? What's the graph of that? Oh, it's not z squared, excuse me, z. What does that graph look like?
Paraboloid.
Paraboloid, absolutely. It's going to look like, right? It's this big old bowl sitting on the origin, right? Now, let's look at what the region is that they want me to look at. They want me to look at, in the xy plane, I'm looking at x equals 0. What's x equals 0? The y-axis. Y equals 1. That's the line y equals 1. Y equals x. Where does y equals x intersect y equals 1? At the point 1, 1. All right, and what's z equals 0? What is z equals 0? This is the x-axis. This is the y-axis. What's z equals 0? The xy plane, right? When z is 0, you're on the xy plane. So they're saying they're taking the xy plane as a boundary, and then they're taking, and this is your xy plane, you see. Where's my region? Can you picture your region? Right here. Okay, there's my region. And where's my bowl? It's sitting right here on top, isn't it? There's my bowl. And so this is your rooftop, this is your tent, right? It's coming up like this, and this is the floor, and you're bringing up these perpendicular walls with this funny swooping thing. On Maple, it looks like this. Now notice I didn't have it draw the whole paraboloid because then it would overpower the picture. I just had it draw the part of the paraboloid that's in the first octant. Okay? And here is your little triangle back down here. It's not imperative that I be able to view that though. The most important thing is I can view this in the xy plane. You guys tell me, how do you want to integrate? Perpendicular to the x? So I say, what is y ranging from? All right, now the integral, it's double integral. The function is x squared plus 3y squared. You want to go with respect to y first and then with respect to x. So the lower bound is y equals x. The upper bound is y equals 1. Sum up all those strips, and what's x ranging from? From 0 to 1. Ones like this on the test, you should say, thank you, Mrs. Strocko, because it's not too much work to do because they're simple polynomials. Okay, we're going to do the inner integral first. Those of you at home, I suggest what you should do is put pause on the tape and do it yourself, and then see if we end up with the same spot. You know, the those of you that are in the studio, unfortunately, you can't turn me off. You're stuck right now, but that's okay. Okay, I'm integrating with respect to x, so y is a constant. So the integral of x squared with respect to x is, oh, was it with respect to y? Oh, you're right. Okay, x, oops. X is a constant because we're integrating with respect to y, and so this is going to give me x squared is like a big old 5, so I'm going to have x squared y, right? And then I'm going to have plus y cubed. All right, and we're going to be integrating from y equals x to y equals 1. So now we're plugging in a y equals 1 here, and we have x squared times 1 plus 1 cubed minus, now we're putting in x in for y, so it's x squared times x, which is x cubed, plus x in for y gives me x cubed. So it looks like I have x squared plus 1 minus 2x cubed. Okay, everybody all right? Now what are we going to do? We're going to take that x squared plus 1 minus 2x cubed and put it in the inner integral. So we're going from 0 to 1 dx. And again, you guys can do this. This is just, you're going to get a 1/3 x cubed plus an x minus 1/2 x to the 4th, and you're going to go from x equals 0 to x equals 1, and a few minutes later we'd be at 5/6. Okay? Okay, good job. Let's look at the next one. By the way, yeah, I already showed you that region there, so that's good. Let's look at the next one. This one, find the volume of the cylinders z equals x squared, y equals x squared, and the planes z equals 0, y equals 4. Where's my roof? Z. Z equals x squared is the roof. That's the roof. What does z equals x squared look like, by the way? If you wanted to draw z equals x squared, how do we draw z equals x squared? How do you do that? Aha! You draw z equals x squared in the xz plane. All right, so it looks like y equals x squared. It's going to come down like this. Okay? I don't have a y in there, so I'm going to drag it along the y-axis. And what I like to do is just draw an x and z-axis parallel, put him in here, and it's going to be coming this way. You can sort of see him. Okay? I actually had Maple do it. Looks a little bit better than mine, okay? But we did okay. All right? Now, where's my base? My base is in the xy plane, right? So my base is formed by y equals x squared, z equals 0, and y equals 4. This is just saying your base is in the xy plane, because z equals 0 is just that xy plane. And then we're going to look at these guys in the xy plane. All right? If I actually drew it, y equals x squared in the xy plane comes down like this. Y equals 4 looks like this, and so there's your base in the xy plane. I actually did it in Maple, and you can see there's your base, and here's your rooftop. But in terms of setting up the integration, I think you're much better off doing this picture in 2D. Y equals x squared looks like this. Y equals 4 looks like this. What are these points? Well, y is 4 minus 2 and 2, okay? And you guys seem to be preferring to always go this way first if you can, This is the only way you can go. Notice strips this way. No, 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 you're going from parabola to parabola. That would be a bit of a problem. So instead, you want to integrate. Function is z equals x squared. So it's going to be x squared. And then looking at my picture, we're integrating with respect to y first. What is y ranging from? X squared to 4. And then if we sum all those strips up, sum up this strip, that strip, this strip, that strip, this strip, that strip, what are the x's ranging from? -2 to 2. Okay? All right, this one's not too tedious to do, so I think we'll go ahead and do it. I'm doing the inner integral first. The inner integral first, we're going from x squared to 4 of x squared dy. What's that integral going to be? Beautiful, x squared y, because x squared is a constant. And we're going from y equals x squared to y equals 4. Plug in a 4 for y, I get 4x squared. Plug in an x squared for y, it looks like I have 4x squared minus x to the 4th. I take that and I plug it in to my outer integral. I'm going from -2 to 2 of 4x squared minus x to the 4th dx. So you'll end up with 4/3 x cubed minus 1/5 x to the 5th. You're going to plug in -2 to 2. And again, just to save us some time, not doing tedious fractions, you would end up with 128/15. Okay? Unfortunately, when you do it, you've got to, I mean, I did it too to make sure the book was right. But you don't need to be watching me putting numbers in a calculator. All right, and it looks like that. Isn't that beautiful? Okay. Oh, I love this one. Find the volume bounded by the cylinder. This is the last volume one that we're doing now. Find the volume bounded by the cylinder, y squared plus z squared equals 4, and the planes x equals 2y, x equals 0, and z equals 0 in the first quadrant. Okay, so we're only talking about being in the first quadrant, okay, where x and y are positive. The thing with z gives you your rooftop. Let's draw what our region looks like just in the xy plane. What does the line x equals 2y look like? It's like y equals a half x. Looks like this. So here I have x equals 2y, or y equals a half x. X equals 0 is here. And I go, oh my goodness, I don't really see a region right now, Mrs. Strocko. They're not giving me something to close it off. Okay, let's look to see why. Let's draw what this cylinder looks like. Okay, but you see what x equals 2y looks like? Okay, and x equals 0 is right here. Okay, so I guess the region's over here someplace, but they're not giving me the border here. Let's see why they didn't. What does y squared plus z squared plus equals 4 look like? It's a cylinder. It just has a y and a z in it, so I draw the graph in the y-z plane, right? And then drag it along the x-axis. Y squared plus z squared equals 4 in the y-z plane looks like a circle of radius 2, right? Because r squared's 4. So my radius is go up 2, go out 2, go back 2, go down 2. Okay? Now, they have z equals 0, which is the xy plane, as one of the borders. You know, your xy plane is your floor. So I'm not going to draw my cylinder all the way around. I could, but it would drive me a little bit wacko. I'm just going to draw the top half because the floor is the xy plane. So we have this cylinder doing this. Now if I drag him along the xy plane, drawing the x-axis, excuse me. 2, 2, 2, 2, 2. Back 2, over 2. That should have been straighter. I apologize. I can erase it because I did it in pencil. Making that straight up. 2, 2, 2, We're going to drag this to here, drag this to here, drag that to there. Okay. All right, look, guys. Where's the line x equals 2y? Notice this is y equals 2 right here. When y is 2, what's x? 1, 2, 3, 4. Here's the point, 4, 2. Right? Because when y is 2, x is 4. Do you see this? You've got this line here. Now if I slice it perpendicular, here's your rooftop, here's your floor. Do you see it? You see it? Here's your rooftop, and here's your floor. Your floor's down here. Okay, so now wait a second. Where's the extra side that they didn't give me? This line right here. That's formed by the cylinder. And what is that line? That's the line y equals 2. This is my region. Because remember, this is your y-axis, this is your x-axis, and remember, I wish I had a... Here's your cylinder. Here's your cylinder. Drag it along the x-axis. See that? Dragging my cylinder along here. So there it is, and that's your floor. Okay? Now, first of all, we have to solve for z to figure out what our rooftop is. We have y squared plus z squared is 4, or z squared equals 4 minus y squared, or z equals square root of 4 minus y squared. Everybody okay with that? So that's what your f of x, y is. So I'm going to be integrating square root of 4 minus y squared. Now, how do you want to integrate? I know, you always want to go with respect to y first. Okay. You could go with respect to the x-axis, people. I'm looking at what I wrote out before. I did it that way too, but you want to always go this way. Now notice, if this is the line x equals 2y, you got to solve for y. Y equals 1/2 x. So we're going to be integrating from y equals 1/2 x to y equals 2. And we said, what was this point right here? I think it was 4, 2. So if we sum up all our x's, oh, this was a good one. I'm glad you guys picked this. If I sum up all my x's are ranging from 0 to 4. All right, now those of you that had me for Calc 2, piece of cake. This is trigonometric substitution. Y equals 2 sine theta. And you're more than welcome to go through and do that. All right, because you'd get a 4 minus 4, but you'd have to put in for dy, 2 cosine theta. Let's do it the other way. Yeah. All right? But, by the way, I wanted to mention to you, and I mentioned this to people coming in for help with their homework. It is okay if you have like an integral of x sine x, or an integral of x e to the x. You with me? Or x, or even an x squared. If you look in the back of your book and they have trig tables, and they say the integral of, or even put in arctan x dx, and you look in the back of the book and they tell you what the answer is, that's not cheating. I mean, we have so many things to do that always doing it by integration by parts and use substitute. I mean, sometimes you got to do use substitutions, but it's okay to use those as tools. You with me? All right. Look in here. Ms. Strocko says, I still know f of xy is square root of 4 minus y squared. You guys didn't want to do the trig substitution y equals 2 sine theta, so let's see if we integrate with respect to x and then with respect to y, if the problem will be a little bit easier. With respect to x, we have to say, how does x change? X is changing from 0 to x equals 2y. And then if we sum all those up, y is changing from 0 to 2. All of a sudden, people, let's look at that inner integral. Looking at the inner integral, y is a constant. So square root of 4 minus y squared is just acting like a 5. So what's the integral of 5 dx? 5x. So it's going to be square root of 4 minus y squared x, as x ranges from 0 to 2y, because that's a constant. You could have just said it's a constant, I'm bringing him out, and just put a 1 there, right? And the integral of 1 dx is x. Popping in the 2y, I get square root of 4 minus y squared times 2y. Popping in the 0, you get minus 0. And look, people, this isn't bad. If I put this in for my inner integral, I end up with, put it in for the inner guy, the integral from 0 to 2, I'm going to write it as parentheses 4 minus y squared to the 1/2 times 2y dy. U substitution time, huh? You can let your, what are our U substitutions going to be here? I'm going to let 4 minus y squared be u. So du is minus 2y dy. So I say, oh, piece of cake. So this is becoming integral from 0 to 2 of u to the 1/2. To get du, I need a minus here. So I'll put a minus here. So this becomes minus du. Or here, if you wanted to solve for 2y dy, just multiply through by a minus. And you can see that 2y dy becomes minus du. And now the rest is history. This is going to be equal minus, increase your exponent by 1, divide by the exponent. Is that right? Which is going to give me minus 2/3 times, what's my u? 4 minus y squared, to the 3/2, as y is going from 0 to 2. And that gives me minus 2/3 times, if you put a 2 in here, you get 0. Minus put a 0 in here, you get 4 to the 3/2. What's 4 to the 3/2? Square root of 4 is 2. 2 cubed is 8. So I have minus 2/3 times a minus 8, which is 16/3. So this is an instance where changing the order of integration made life, I mean, we're getting tired, but at least we could do it. Okay, that's enough of those. Let's move on. Oh, by the way, I took this y squared plus z squared equals 4. Here's your cylinder, dragging it along the x-axis. Here's my little, here's the line y equals 2, or x equals 2y. I also put the line y equals 2 in there, and you can see your little region is right in here. Okay, all right. Here, sketch the region of integration and change the order of integration, because there are many times, especially if you're in the applied sciences or in engineering, where you might have an integration to do in one way, and you're beating your head against the wall and you can't do it, and you want to try it doing the other way. Notice they're telling you f of x, y. They're not telling you what the function is. So good news is we don't have to do the integration. Okay? All right. First of all, you've got to be able to draw the region. The inner region, y ranges from y equals 4x to y equals 4. You with me? Because your y is ranging from 4x to 4. Y equals 4x looks like straight line. Y equals 4, horizontal line. What is their intersection point? What is this point right here? Well, if y is 4, I guess x is 1, right? Okay. Now, what's x ranging from? X ranges from x equals 0 to x equals 1, doesn't it? So if we're going to go from here's x equals 0, and here x is equal to 1. So we're saying inside the region, y is ranging from 4x to 4, and then we're letting our x's range from 0 to 1. So if we wanted to change the order of integration, before it was dy dx, we want to do dx dy. You're going to have to say, how does x change? It changes from here to here. This one, I'll tell you, is 0. But this line right here was y equals 4x. If you want to know what x ranges from, you've got to solve for x. And then summing up all those strips, what is your y ranging from? 0 to 4. Okay? We can't do it because they didn't tell me what the function is. Okay, let's look at this one. In this one, x is ranging from 0 to square root of 9 minus y. Okay, x is ranging from 0 to square root of 9 minus y. Okay, what does that look like? X, I don't know what x equals square root of 9 minus y looks like, do you? Good job, let's square it. That gives me y equals 9 minus x squared. Oh, what is that? It's a parabola. It's an upsy or a downsy? He's a downsy. How high does he go? 9. You guys are good. So he's going all the way up to 9, and he's a downsy. Now, normally, we would draw that whole thing like this, except the original equation, since it's x equals positive square root, we're only going to draw the part where x is positive. Okay? So we have x ranging from the y-axis to the parabola. What do we have y ranging from? 0 to, now remember this was 9. Y is just ranging, from 0 to 3. Okay? So my region looks like this. This curve right here is y equals 9 minus x squared. What's this point right here? Well, y is 3. If y is 3, can anybody tell me what x is? Good, because you put a 3 in for y, you're going to get 3 equals 9 minus x squared, or x squared is 6, so right, that's square root of 6. Okay, now they want me to do the integration with respect to x, with respect to y. Is that right? No, they want me to go with respect to y, with respect to x. That's not such a good idea, because look here. If I go with respect to y, look here. Here, your y is going from bottom line to top line. No problem. Here, we're going bottom line to top line. Here, bottom line to top line. Uh-oh. Do you notice, in this little itty-bitty section here, I'm going from here to, parabola time. What do you think I got to do? I need 2 integrals. This x right here was square root of 6 because we go over square root of 6 up 3. So we have to do 2 integrations. We're going to do the integral over the box. This region here. You see this region right here that I'm covering in? And then we're going to do this itty-bitty region right here. And the sum over this box plus the sum over the green guy adds up to the sum over the whole region. So we'll go double integral of f of xy, we're doing dy dx, of region 1, plus double integral f of xy dy dx of region 2. Region 1, what's y ranging from? 0 to 3. And if we sum all those up, x's are going from 0 to root 6. Now, in the little bitty green guy, what's y ranging from? From 0 to 9 minus x squared. And if we sum all those up, the x's are ranging from root 6 to, I don't know what that point is. That's on y equals 9 minus x squared. Y is 0, right? Well, if y is 0 right there, right, it's 3. Done. Okay? All right. Yeah, we better, we don't have to evaluate it. I just want to talk about it. This one, U substitution for this guy is not going to work. U substitution for this integral is not going to work because you let your u equal x cubed plus 1. Your du is 3x squared dx. I can't see an x squared. It's not going to work. But if you notice, if you change your order of integration, right now your x is ranging from x equals square root of y to x equals 1. Most of you have no clue what x equals square root of y looks like. How can you find out what it looks like? Square it. Okay? So we're going from y equals x squared to x equals 1. If this is y equals x squared, what's this point right here? 1, 1. All right? So x is ranging, in this integral, x is ranging from square root of y to 1. And what's the y's ranging from? From 0 to 1. That's my region right there. Now let's change our order of integration, but we're not going to do the whole integration because I can tell you guys are getting a bit tired. The integrand does not change. The integrand is just copying him. I don't like that pen. I like the green the best. It's x cubed plus 1, and we want to do dx dy, right? Oh, you're right. We want to do x cubed plus 1 to the 1/2 dy dx. Coming back and looking at our region, what is y ranging from? 0 to x squared. And what's x ranging from? 0 to 1. Now let me just to have it hit home why this is better. When you do this inner integral, what is x cubed plus 1 to the 1/2? A constant. You're integrating with respect to y. You can put that sucker out here if you wanted to. You're really integrating 1 dy, so it's going to be the constant times y. And we're going from y equals 0 to y equals x squared. You're going to get x cubed plus 1 to the 1/2 times x squared minus, you put the 0 in, you get nothing. Then you take this and you plug it into the second guy. Can I do that? What's my u going to be? My u is going to be x cubed plus 1. My du is going to be 3x squared dx, right? So my x squared dx is just 1/3 du. So this becomes the integral of 0 to 1.
Would it be a minus 1/3?
Why a minus 1/3?
If there's a minus.
Where's a minus?
It's minus x squared.
No, it's times.
Oh, that's times.
Yeah, that's a times. That's a times. All right, and so I'm going to put in a u in, so I have u to the 1/2. And for x squared dx, I put in 1/3 du, which gives me 1/3 times u to the 3/2, and dividing by 3/2 is the same as multiplying by 2/3, which gives me 2/9, and u was x cubed plus 1 to the 3/2 from x equals 0 to x equals 1, which gives me, factor out your 2/9, popping in a 1, 1 plus 1 is 2 to the 3/2, can't do much with that, minus popping in a 0, 0 plus 1 is 1, 1 to any power is 1. Okay, now we've done a number of those, but the point is changing your limits, your order of integration is very important. I'm not going to do any more problems, but I just want to comment. As we had to do in that one problem, sometimes you've got to break up your region into two regions. If you do your integral of f of xy over the first region plus your integral over the second region, it will be the same answer as if you do your f of xy over the whole region. Okay? Next thing, note, if for f of xy you let it be 1, what you're going to actually be finding is this area. Because if you think about it, when you're doing your double integral of f of xy dx dy, if that f of xy is a 1, if you think about it, you're summing up 1 times delta x delta y for all your little subregions. You break this up into your little, for each one, if you go delta x delta y, you're just finding the area of that one little region. You sum them all up, you're just finding the area of the region. So you can use a double integral to find the area of a region. Thirdly, if your height, your f of xy, can be sandwiched between two constants, little m and big M, it only makes sense that this A of D means your area of the region. If you make your height be m times your area of your base, that'll be less than or equal to your double integral, which will be less than or equal to your maximum height times your area. Because this is a height that's less than or equal to your f of xy, and this is a height that's greater than or equal to. So if your roof's somewhere in between, your volume will be between those two. If you think about it, if you don't like the way I wrote it, let's do it this way. You could say if m is less than or equal to f of xy, which is less than or equal to m, then the double integral of m dA is less than or equal to the double integral of f of xy dA, which is less than or equal to the double integral of m dA. Here you could factor out your m, and remember we just said the double integral with the function just being 1 gives you your area, so it would be m times the area of your region is less than or equal to this double integral, which is less than or equal to m times your area. Because this, again, if you factored out your m, double integral of dA is just going to give you your area of your region. For homework, it's very important for you to look over the examples on 1031 to 1037, and then on pages 1038 to 1039, you need to look at 7 through 19, the odds, 23, 25, 27, 37, 39, 43, and 45. Okay, I'll see you next time.